Okay, so in this video, we'll talk about the quantum Fourier transform and essentially tell you why it is more efficient than the classical Fourier transform. So we'll try to look at a lemma that makes this efficiency possible. So let's dive right into it. So we define a Fourier transform as an n-dimensional unitary operator that goes from the n-dimensional complex vector space to an n-dimensional complex vector space. And suppose I have a basis x1, x2, xn of my vector space, and xj can just be 0 everywhere else. So it could be the standard basis and 1 on the jth coordinate, right? So the Fourier transform transforms this basis into another basis. So yj the gets transformed under this, I should say, x. The basis goes through a transformation, and the new basis under this Fourier transformation is the Fourier basis, which looks like this. So each element is defined as 1 over square root of n summation over k going from 0 to n minus 1 e to the 2 pi I j k x k. So this is a new basis, and this is also an orthonormal basis since Fn is a unitary transformation. Okay, so now one has to think in terms of qubits. So if I have an n-dimensional space, then if I want to represent them in qubits, then I'll require little n number of qubits, where capital N is equal to 2 to the power n. So how do I represent these basis vectors? Right. So for example, let's take the case of C4. So there are 4 basis vectors, 1, 0, 0, 0. So in C4, there are these basis vectors 0. There are 4 basis vectors 0, 0, 1, 0 and 0, 0, 0, 1. So these are 4 vectors, each of them a 4 cross 1 vector. And if I want to represent them in qubits, I only need two of them. So I can represent this vector as 0, 0, tensor 0, then this vector as 0, 1, this vector as 1, 0, and this vector as 1, 1. Right? So n is equal to 4 and little n is equal to 2 over here. So I'll need 2 qubits to represent a 4-dimensional Fourier transform. Okay, so in general, if I have an n-dimensional Fourier transform, which is so n is equal to 2 to the power n, then I can represent them, each of these basis vectors, as j1, j2, jn, where j1 can take the values 0. So this belongs to 0, 1, right? J2 belongs to 0, 1, and so on, right? In this way, if I take the bit representation of these basis vectors, I can represent these basis vectors as n, little n qubits. And so the lemma that I'm going to talk about will be in this representation. So the lemma of, I'll call it the QFT lemma, or quantum Fourier transform. It says that this Fourier transform that I have defined over here, if I convert this into the qubit representation, then it works out like this. So the Fourier transform is just this basis that I just showed in terms of qubits. So now we have a n is equal to 2n dimensional Fourier transform. And this goes to get 0 plus e to the 2 pi I 0.jn. And I'll just in a minute, I'll tell you what this notation means. Tensor 0 plus e to the 2 pi I 0.jn minus 1 jn get 1. And then similarly, the last one is 0 plus e to the 2 pi I 0.j1 j2 jn get 1. And the whole thing is divided by 2 to the n over 2. Okay, so you might be wondering, what is this 0.jn mean? So jn is either a 0 or a 1. So 0.jn means jn divided by 2. This is the same as that. 0.jn minus 1 jn means jn minus 1 divided by 2. So it's a bit representation in base 2 notation over 2 square and so on. So the main point of this lemma is that in this the qubit representation, this product state, this is a product state. Right? And the Fourier transformation takes this product state to another product state which looks like this. And this is used to simplify the circuit for the Fourier transform. Right? So let's prove this lemma. I mean, let's make sure that we have understood the statement of the lemma. So we have a capital N dimensional Fourier transform. I can represent the capital N basis vectors in terms of qubits, where little n is the number of qubits. Then in the basis qubit representation, I have this basis vector, and the lemma states that this basis vector goes to this product state, where this representation that I have shown over here, 0.jn means a base 2 representation of the bit jn. Right? So let's prove this lemma. Recall that we started out with this definition of a Fourier transform. So this is our original definition of our Fourier transform. And then we went from to a qubit representation, and we got this lemma. So this is specific to a quantum computer because we can represent qubits. We can best represent basis vectors as qubits and so on. So let's try to prove this lemma. So let's start with the original Fourier transform. So proof, what is the Fourier transform is defined, a basis vector j goes to, now I'm going to change to the qubit representation slowly. So this is going to be summation k equal to 0 to 2n minus 1. So we'll always assume 2 to the power n is equal to capital N, e to the 2 pi I j k over 2 to the power n and k. So now I'm going to go to the qubit representation. I'm going to write k as some k1, k2, kn, right? So this in the next step, so J1, this is my qubit representation of J, Jn is equal to 1 over 2 to the n over 2, summation k equal to 0 to 2n minus 1. And then over here, I'm going to write k1, k2, kn. And since I'm writing k1, k2, kn over here, instead of this summation, I can write a summation which runs over summation k1 going from 0 to 1, summation k2 going from 0 to 1, summation kn going from 0 to 1, right? This will take care of all the 2 to the power n combinations. And then over here, right, we have k is equal to summation in the bit representation, summation kl 2 to the power minus l going from 1 to n. So I'm going to replace that over here. So this is, so I'm representing this k in the binary representation. So this will be e to the power 2 pi I j k. There will be a summation in the top as well. Summation L equal to 1 to n k L 2 to the minus L, and the whole thing will get divided by 2 power n. Right, this is all in the exponent. But notice that this is in the exponent, so I can use the fact that e to the power a plus b is equal to e to the power a times e to the power b. So in the next step, I'm going to do this exponent, change this exponent. Okay, so here is my next step. So J1, J2, Jn. This should not be equal to, but rather this under the Fourier transform goes to f. This is going to be 1 over 2 to the power n over 2. Summation k1 is equal to 0 to 1 dot dot dot. Kn is equal to 0 to 1. And then I'm going to have this product symbol pi, which is the product symbol. This is going to be L going from 1 to n e to the 2 pi I j and then kl over 2 power L. And then I can write this as KL. Right? So or I should rather write this as K1, K2, and Kn. Right? Okay. Good so far. Now, next step, I'm going to write this n 1 over 2 to the n over 2 summation k1 is equal to 0 to 1, kn is equal to 0 to 1, I can write this thing as a tensor product, right? I can factor these things as a tensor product. So this will be tensor L equal to 1 to n e to the 2 pi I kl over 2 to the power L, and this will be kl. Okay. The next step is the most crucial one. The tensor product is a distributive thing. So if I have A plus B tensor C plus D, then I can write this as A tensor C plus A tensor D plus B tensor C plus B tensor D. This is the distributive property of the tensor product. So the most crucial step in this proof is to be able to interchange the tensor with the summation, right? And what we have on the right-hand side over here is this form, right? The distributed form. And I'm going to sort of factor it by interchanging the summation and the tensor. So the next step is interchange the summation. So the J1, J2, Jn goes to F capital N. This should be 1 over 2 to the power n over 2. And then I'm going to write the tensor first. So this is tensor. It's going from L equal to 1 to n. And then I'm going to write the summation after that. So this is interchanging the summation and the tensor because of the distributive property of the tensor product to 1 e to the 2 pi I j k over 2L, and this will be KL. Okay, so I did that and we are almost done. Now I can write this part as, so this is going to be 1 over 2 to the n over 2 tensor L equal to 1 to n. Well, when KL is equal to 0, this will be just ket 0. When KL equal to 1, this will be e to the 2 pi I j over 2L and ket 1. Right? So now we have this product form. And well, we are not yet quite done. The final step is to get it into this form, right? We have this point Jn and point Jn minus 1, right? So how do I get that? Well, over here, if I see it, it is j over 2 to the power L. Now, suppose I now convert to the decimal form. So J1, J2, Jn over 2L. If you divide it by, let's say L is equal to 1, right? Suppose L is equal to 1. Suppose I divide it by 2, then this will go for L equal to 1. This will be J1, J2, Jn minus 1 dot Jn. Right? Just like when you divide by 10, you take the decimal point. Suppose I have a number A, B, C, and you divide it by in the decimal representation. If I divide it by 10, it will become A, B dot C. Now we are in the binary representation, so I'll get this. And then I can ignore this because we have e to the 2 pi I j1, j2, jn dot jn, right? And this just gives, since this is e to 2 pi I multiplied by some integer, it'll always be equal to 1. So we can ignore this, and I can write this as just e to the 2 pi I 0.jn. And that leads us to this final step, which, so j1, j2, jn goes under the Fourier transform as 0 plus e to the 2 pi I. When L is equal to 1, I'll get 0.jn. When L is equal to 2, I'll get 0 plus e to the 2 pi I 0.jn minus 1 jn, get 1, and then so on. And the final one will be 0 plus e to the 2 pi I 0.j1 j2 n, get 1. All right, so that's the main lemma of the quantum Fourier transform. We have a qubit representation, which takes a product state basis to another product state basis. So basically, essentially, this qubit goes to this qubit goes to this qubit, and so on. So it gets factored into this. And in the next video, we'll see how this lemma can be used to devise a efficient circuit for the quantum Fourier transform.